I want to talk about generic derivation because generic derivation, type class derivation, because it's a topic that a lot of people are really interested in. And I think that generic derivation is a really, really powerful new thing. And it's powerful enough to basically replace a lot of reflection use cases with things that are just much better performing and more ergonomic to use in certain cases. In Quill, I use it in a whole bunch of places, and it's just really, really good. A lot of people have implemented Json encoders and decoders, and we'll look at a small example of that. I think that it's almost as though they say that word count is the hello world of Hadoop. Well, a JSON encoder is the hello world of generic derivation in a sense. But anyhow, so let's jump in. So first of all, I'm going to be showing you a bunch of benchmarks. Benchmarks don't actually mean much if you don't have anything about the spec of the machine that they were on. So whenever I show you some numbers, just keep this in mind. And all of them are with Scala meter that I think works on top of JMeter. And we've got some warm-up runs and some benchmark runs. And all the numbers assume a 15% of the mean standard deviation, even after all of these warm-up runs. It's still the standard deviation on them is still there. So just know that that's the every number plus minus 15% at least, and that's if you have the same system spec. So all metrics must be taken with a grain of salt. That's the reality of it. But anyhow, let's talk about Java reflection, right? Because that's what we started with, right? But before we go into Java reflection, we kind of have to, understand what our baseline is of what, of when you're reflecting on something, what's the best that you can expect? And the best that you can typically expect is based on the underlying data structure that you're using. So here, for example, is a unholy, impure, mutable data structure. We utterly despise these things. Their eyes are pools of terrible fire. Their terrible whiskers are tougher than wire, et cetera, et cetera. But they're pretty darn fast, right? Doing inserts in this thing is pretty darn fast. Now, we really don't like that. So, let's look at the immutable version of that. And guess what? That's like almost twice as slow. So that's a reality that we have to deal with immutable data structures. If you've looked at Dmitry Petroshenko's talks all the way back in like 2016, where he talks about the beginnings of doing what he called back then Scala Blitz, this is a big issue because there are a whole bunch of allocations in here, potentially boxing and unboxing. They've improved a lot of this in Scala 3, but still, it's not able to do what we could do with mutable data structures, at least in this form, not yet. So when we talk about doing metaprogramming, what we want to have that low number. We want essentially to be able to produce something that is the equivalent or almost is the equivalent of a mutable data structure with handwritten code. That's what we want to happen from metaprogramming, right? Because metaprogramming is essentially we are generating the code that will come out. So we want to aim for as efficient code as possible. And then we can wrap it into something immutable a little later potentially, but we really want performance to be up there. And we can, it is possible. And then when you add actual Java reflection to the picture, well, then it gets really bad. Then it's like, it's not twice as bad, it's 10 times as bad, right? Like this is actually doing reflect and going through reflect fields is just very, very, very inefficient. So typically the approach, you look at things like the Apache Commons libraries and stuff like that. They try and cache things as much as they can and have these awful global singletons that do all that stuff. Preferably, we'd like to avoid approaches like that if at all possible. You need to, if this is 10 times as bad, in order to be able to effectively amortize this, you have to have 100 times as many lookups of whatever cached version of this you're going to use in order to flatten that out. So it's okay. For some applications that's possible, but not necessarily for all applications. So the approach in Scala has always been to use macros, Scala 2 macros, Scala 3 macros. We use a macro in order to be able to account for this. So here's a Scala 3 macro. Now, something to understand is that Scala 3 macros are, although they can be nasty in some places, they are substantially better and substantially more ergonomic than Scala 2 macros, right? So we're doing a symbol lookup here. So this is essentially a field reflect, right? So we reflect the type of this thing of person, right? T is person. And then we go through the case class fields. Okay, we get the value by doing a dot select on it. We get the key by doing the name of the field. Okay, fine. And we'll put the key and the value in our hash map. And then we take every single one of these puts and we wrap it into a block. Or take all of them and wrap them into a block, right? So what happens as a result of this? Okay, so here we go. Reflect it, take the key and the value, put it in. What happens? There's our block. Oh, that actually gets swapped into this call, right? This is macro. Inline def, this declaration inline def, whenever you see inline in Scala 3, that means it's a macro. So this code will actually get swapped into there. So the equivalent is that. That's what our code ends up being when we've called this macro, right? These are the insertions. Okay, fine. And this will be 91 nanos, as though it was hand-coded, okay? So the next thing that we can do is that we can just take this, wrap it into yet another inline method, because inline methods will call inline methods, and then essentially the code substitution will happen recursively. One will nest into the other, will nest into the other. Okay, fine. And then what we can do is we can take this mutable map, we can give the user an immutable view, and essentially, right, that's what's coming out now. And we have a function which essentially is immutable, gives us back something that's essentially immutable, and it gives us almost the performance of immutable data structure. Okay. This is nice, but it's a little bit of a toy example. In reality, with reflection, we typically need to have data structures that reflect hierarchical objects, right? Whether eventually we serialize them into JSON or into binary structures or to whatever, we need data structures that can represent type hierarchies in some sort of way, right? In this case, we have person, and person has this name object, and the name object has fields. And so, okay, fine, that's one way to store it in a reflective way. And then we'll do things, again, we'll do things with this, like encode it in some sort of way or do something else with it to derive some business logic. But whatever our reflective system is that generates its data structure, it needs to actually know, oh, when you look at a person, look at a name. When you look at a name is another case class or another product type. And then we need to actually go and recursively be able to extract the structure. So, okay, fine. That gets a little bit more complicated, right? So we've got, now what we need to do is instead of just getting the initial case class, we need to get the case class, we need to go through the fields, we need to look at every single field to see if it's a product. And then once we do that, we say, okay, fine, is it a product type? Then actually recursively call this reflective structure stuff during compile time. There's a little bit of sorcery if you see the syntax, like what the heck is this? This is essentially an extractor on a type in Scala 3 macros. This is essentially a syntax that lets you extract a type variable. And we're not actually doing any logic in the extractor, but this is essentially a syntax that will let us take this thing and then plug it into the hole for the type into this recursive call. So, and then we call this thing recursively and it goes on. So let's go through that. Okay, fine. So we've got a product. There's the voodoo that we just mentioned that we need to use to pull this thing out. Okay, then we call this thing recursively, and okay, voila, there's our recursive macro, which will be able to reflect over our types. And then this, right, there's what you do to call the macro. Okay, 157 nanos, that's nice. Here's the equivalent of having it done by hand, same performance. So we're still in a place where we can have the equivalent of handwritten performance that's done by a macro. And again, this is basically giving us, once we take this thing and we wrap it into an immutable wrapper, this will give us a immutable data structure that we get out of this thing, and that will give us the equivalent of handwritten code. Thing is, though, there are some issues, right? Let's say that the user wants to extend their type system with some kind of custom data type, right? Let's say that we want to do that. Well, that's not the correct reflection. Oh, but this is a product, right? Our logic for products is that we recurse, and every single level of a product type is going to give us another map. Okay, so we need to account in our system for potentially user-defined types. And this gets a little nastier and nastier and nastier, because suddenly we need to summon, potentially we need to summon other things that the user might have declared in our macros and check those, and they get nasty very quickly. So that's right, that's not what that's supposed to be. It's just supposed to be 1, 2, 3. Right? Essentially, this is a user-defined type. UDTs. Funny how Spark still doesn't really support them. Anyway, moving on. So the other issue is that we have to deal with some kind of polymorphism, right? Let's say that, for example, the user of whatever we're doing wants to define some kind of name thing, which could be a 2-part name or a 3-part name or whatever. Right, we have to actually figure out, oh, this is this, and this has these subclasses. And then we have to go through the subclasses and all the possible fields of all the subclasses, and then reflect on those. And this really turns into a nightmare, because then you actually have to walk through arbitrary type hierarchies inside of your macros. This really gets bad really, really quickly. So if we could rethink reflection from the ground up, right? If we were actually able to do that, well, here are some of the things we'd want. We'd want it to be fast, right? Or we'd want it to basically be the equivalent of, once it's done, producing what is handwritten code. We want it to have an extensible type system of some kind. We want it to be able to account for polymorphism. So this is essentially what generic derivation is. This is generic derivation, type class derivation. That's what this thing is, right? So it's fast because at the end of the day, it's built on top of compile time macros. It's extensible because it's composed with type classes, and it's polymorphic because it uses coproducts to achieve the polymorphism, which we will go into very soon. First, however, we need some prerequisites. And so what I will show you a little bit later won't look like complete sorcery or gobbledygook. A couple of things, right? In Scala 3, you have this tuple consing operator, right? This is equal to that. A tuple An n-ary tuple can be represented by this sort of cons tuple structure. Now, you can actually evaluate this thing, and this evaluates to that. So you can do it. In the actual Scala AST, the Scala's own AST, right, there's a separate AST representation for this and for this. It's only in the evaluation that these things are equivalent, but you can, during compile time, even sort of map between the two fairly reasonably. Now, the other thing, the even more interesting thing, is that this consing operator can be used for decomposition. So we can actually decompose a tuple into pieces of it. Okay. So now a couple of other things, right? We can match on a type, right? We can match this tuple on a type. Now, this gets a little tricky because with type erasure during compile time, right? How do we do a type match if it's with type erasure? Well, if you have an inline function, well, guess what? That inline function is not running at runtime. That inline function is running in compile time, which means you do know the types because they haven't been erased yet. So, and this will actually give you a warning if it's in a runtime function. Oh, we might not necessarily be able to do that, but in an inline method, this is perfectly fine. Now, we can also match these things. We can also match these things by a regular type, right? This kind of match is the equivalent of this kind of match, right? Because again, this is the tuple consing operator, right? This is the equivalent of that, okay? Now, here's the other thing, right? If we are just matching by type, we don't actually have to grab the instance of the thing, right? We can just say, okay, match it by the type. Does the type match, right? And so here's an example of that, right? We can say, does this thing actually match the type that we have? Now, there's one more interesting thing that we did here, which is we used a wildcard. So the syntax that they've decided to use is that all types that are lowercase, that don't start with a capital, inside of these extractors, the lowercase ones are actually wildcards. And what we can do with these wildcards is that we can take them and we can pass them into other functions as type parameters, right? So this is sort of the equivalent of what I showed you with that quote bracket TPE thing earlier on. This is essentially the same as that. This is a type extractor like that. Okay, so taking it one step further, right? How do you, once you actually pass that type into a function, what can you do with it then? How do you match it on something? Well, in Scala 2, you typically would need to use a class tag or a type tag or some other sorcery in there that would actually give you the information on its type, and then you would use that. Well, in Scala 3, what we have is this thing called erased value, which is, again, something that you can only do during compile time, and you can basically extract a value of a type. Now, you can't actually extract it in real life. That is to say, you can't actually use it. You can't assign it to something, really. But what you could do is you could use it to match things. So you could match the type that is coming out of here, which is the type that was plugged into this function, and you can actually match it on something. So, and yes, as I said before, erased value can only be used from an inline method, i.e. a macro. So, right, here's an example, right? That's what happens when you pass that in. Now, here's the interesting part, right? So this is what we do. And again, this is a macro, right? Macros happen during compile time. So this case actually gets swapped in to your code. So if you do print line of this thing an int or string or whatever, right? Actually, that's wrong. This is supposed to be int, but anyway, this thing actually gets swapped in, and this is the code that you end up with. Sorry, it's supposed to be int, not string. I made a mistake on the slide. Anyway, so, okay. Now, next part. You can use erased value and match type together with deconstruction with the consing operator with a wildcard. So, you use this thing, and then once this type comes out, you can then pass it to other functions, and then use erased value and match and those things as well. Now, where is all of this going, right? I'm giving you more and more interesting variations of stuff, but what's the point of all this? Well, you'll see in just a minute, but here's the beginnings of it, right? Why are we doing this? Why are we taking types and then type matching them and pulling them apart and then using them to summon stuff? Here's why. Because this can operate on our type classes, right? We can create a hierarchy of type classes and type class instances, right? So fooable, let's say, is our type class, and these are type class instances using given and with, and this is the, this is the Scala 3 way of doing type class instances, which is pretty. It's certainly prettier than defining it with implicit defs, right? So these are type class instances. So what we can do is we can then take a type, put it into here, extract the members of the type, if it's a tuple, right? We're assuming that this is a tuple. We can extract its members, in this case, the first thing that the tuple will have, and then use that thing to summon a type class. So here's an example, right? Let's say we match summon type int string. Guess what? It will summon the int fooable, right? The int goes inside, right? That's what the prefix matches. Then we use summon inline to summon a fooable instance out of that, and then we call the fooit function on it. So that's what this stuff does. Furthermore, we can use this approach recursively, right? We can recursively walk through a tuple and summon type class instances for every single member of the tuple. Okay, so here's, right, we're recursively summoning instances for string int string, right? So we put in this tuple, right? String int string goes into here. We pull out string, right? Then we summon the string fooable. So that's this guy, right? Then it's going to be int string. Those are the next things, right? The next thing is an int, goes into here, summons an int fooable, right? Then only this last string is left, goes in here, gets summoned. That's this guy. What happens after all of them are done? Guess what? Empty tuple. We cons a nil onto the list. Okay. Now, oh, by the way, just FYI, you can do other interesting things like match type holes, right? If it's an option, pull out the type inside the option. Super useful if you want to be able to abstract out optionals, for example, in an encoder. Same thing with filtering. Filtering actually is very interesting. You can define types, and those types actually can act as filters in this thing. But anyway, so let's talk about products and coproducts for a second, right? Here's a product, right? A thing with stuff with other stuff, right? It's stuff and stuff and stuff, right? So a product typically in Scala is represented as a case class or a tuple, right? They're all a product. Case class just happens to have field names on it. There's another example. Now, this is interesting. In Scala 3, we have these things called enums, like really good ones. And each case of an enum is a product, right? And so this essentially, this is like a case class. This single thing is a case class because it's a single case of an enum. So, okay, fine. Coproducts. How did we define coproducts? Right? Coproducts is this or that or that. How did we define coproducts in Scala 3? Well, or excuse me, how did we define coproducts in Scala 2? Well, we had these sealed traits, right? This can be that or that or that. Okay, that's all right, I guess. Not all that ergonomic, but it works. Scala 3, again, we use enums. So a single enum is a product. The whole thing is a coproduct, right? Because this is this or this or this or this. Okay. Now, combining products and coproducts, you can basically describe almost any business domain that you want by nesting them into one another. Now, here's where all this has been leading up to. In Scala 3, there are mirrors. In anything that's a product, you can have a product mirror. You can actually also write custom mirrors, which hopefully somebody will for things like Java Beans, because they're also products, actually. But anyway, you can summon a mirror of a person, and it will be a product mirror. This is not a value. This is a type, right? You can have types have things, right? This has fields in it, but again, it is a type. You get this thing as a type when this thing comes out. There are other things. There are a couple of other things inside of the mirror, but this is the most important in terms of generic derivation, where you have the element types and the element labels. The same thing for a coproduct. The element types will tell us all the possible things that coproduct can be, right? So this food can be 3 kinds of things. So the mirror has the 3 kinds of things that it could be as a tuple. What we can then do is summon these products and coproducts and put them into recursive functions that use the consing operator and summon a type class for every single one of them. So in a product, they can summon a type class for every single element of the product. For a coproduct, they can summon a type class for every single possible element of the coproduct. We're about to go into that. So let's start with our object that we had from the beginning. Right, so we want to have a right to map, right? That's the thing that we're reflecting on. Okay, so there it is. And we say, okay, this thing is derived. This is our derived generic. Now let's start with this mutable map. We'll put it into an immutable wrapper a little bit later on. All right, so let's put that in. And then let's summon the right to map for that person. And then let's actually invoke it. Well, what happens? Okay, so here is how we actually write the derived version of right to map. Right, imaginably, there's a right to map for int, there's a right to map for string, right? That's pretty easy, just write the key and the value in. Well, here's the derived version. Okay. So here we put person as T, right? And then the labels, mirrored element labels, become these. Mirror element types become these. And these are the types that get plugged into our functions that will then recurse over them. This one will recurse over the labels and just pull them out. This one will recurse over the types and summon a right to map type class for every single one of these types. Okay, let's go through that. First of all, right, we need to actually figure out what kind of mirror it is, assuming that it's a product in this case. Now, go through the mirror element labels, right? This is first name, last name, age. Okay. Then go into the recursion. There's our recursion. Okay. Oh, so pull out the first thing, right? First name is the first element, pull it out into this. And then we have this funny little thing called const value that will give us the label. And then it will actually give us the label as a type as opposed to as a string. So we have to use .toString to actually make it into a proper string. Fine. And then what we do is we want to return this into a list, and we use the list cons. And then guess what? We recurse. Okay. Next element of the tuple, right? Last name and age is what's left. Okay, let's pull out last name. Let's use const value. Again, to string it, call the recursion again. Finally, age is left. Take it, pull it out, recurse. And there we go. Empty tuple, cons a nil onto it. We're done. And that's what comes out. So that's the list of our names that's going to come out. Now, here's the more interesting part. We're going to go through every single type of this product and summon the right to map type classes for every single one of those, right? So here's the one for int, here's the one for string, right? Okay, let's go through them. String, string, int. So the first one is a string. And now we summon this right string out of it. So summon writer, by the way, is nothing but summon inline. That's what this thing just does. So, okay, it'll summon this right string. So we've got a string writer. We go to the next type. We've got a string writer again. Okay. The last type, which is an int, we summon the int writer, and then we're done. So now we have the writers. Now we've summoned the writers. So we've summoned the writers, or excuse me, we've summoned the labels, we've summoned the writers. Now all we have to do is zip them together, and we have to combine them. And while we have that, what we also need to do is we need to actually pull the values for each of these labels out of our T person, and then actually plug them into these writers. That'll put them into that hash map that we've got. In order to do that, well, the simplest way to do it is, well, we know that T is a product, right? Because it has a product mirror, so we can cast it to a product. That's what this thing uses. And then it says, oh, we cast it to a product and get something at that slot. Okay, so then we have a zip of these three things. First name, last name, age. We have our writers and the indexes of the elements that we want to summon from, or that we want to extract from our product, which we will then plug into our respective writers. Okay, and oh, once we zip everything together, that's what it looks like. Okay, fine. So now we have first name, right string, and that's at index 1. So we pull out the value of the person product at index 1. We use the string writer, we write it, and then we put the whole thing, the whole key and the value into the map, right? So that'll be Joe, right? That's the first name. Joe will be pulled out. Then again, the last name, we got that. We got the string writer, pull out the second index from the product, Joe blogs. Now we have our int writer, excuse me, that the slide is wrong. It should be, well, this should be age, and this should be right int, and this should be right int. Sorry, slide is wrong again. So this should be right int age, and the value 3 should be put into there. There it is, and this is also incorrect. That's what that's supposed to be. This is supposed to be right int. Okay, so we're done. We did it. Good, I guess. Right, here's what we have. We wrote it to a map. We're done. Except for the fact that this takes more than twice as bad as our 93 nanos that we wanted to have originally. why does it do that? Oh, by the way, here's our immutable wrapper, right? We took it, wrapped it up into an immutable, or returned a view from it. But that should still be 103 nanos or 105 nanos. Why is it 200? Right? Why is our performance double what we wanted here, or half, whichever way you want to express that fact. Okay, well, we actually look at the code inside of this thing. Wait a minute. So first of all, remember that as we recursed over the labels and the values, we were using a list cons. So remember that inline functions don't actually get evaluated during runtime. They get spliced during compile time. So recursive calls of inline, an inline match, which is what we had there. Well, guess what happens there? They get spliced in recursively. So these are recursive splices. This is what the code actually is, but here's a consing operator. Well, list is a mutable data structure. Consing mutable data structures has performance implications. But okay, fine, this is all right. Right, so there's, by the way, there's what we did for the writers, right? We consed both of those lists together, but it gets worse, right? We use this zip operator. That required an allocation of another list. We then did zip with index. That requires another allocation of a list. Oh, and then the dot map, which is another allocation that I'm technically not even counting because this could probably be replaced with a for each. So, okay, this is a little nasty, right? It makes sense why this is a little non-performant. So can we do better? Well, we can. There are a bunch of things that we could do. The simplest of which is to, this is a neat trick actually. The simplest thing to do in here is to take these two things and then have the erased value of the tuple, the erased value of the tuple together, and then match on this whole thing. This is a really, really neat trick. So what you can do as a result of that is you don't need to produce things and then get back values and then zip them with other things, right? We can all in one, we can get the key, we can get the value. And then once we've got that, we can summon the writer from the value, from the value type, which we have. We then summon it, we write the value in, and then we recurse all in one. So we don't need to do any consing. We don't need to do any zipping. We just all in one recurse, write, recurse, write, recurse, write into our mutable data structure. So, and then we just call this thing just once in. So match the mirror type. Is it a product mirror? Go into here. Get all of the element labels, get all of the types. Voila. Put them in. Right? Put them in. And then match on them. Pull out the values. Get, right, like we did before, get the const value of the key. Okay. Once we've got that, well, then we just need the actual value of the element, which we do. And by the way, notice that the argument to this function is an index, right? We actually use an index, and then that index actually shows us what position of the product element to pull the actual value. Okay, so once we've pulled out the label, once we've pulled out the value, well, we just summon the writer, write it into our mutable hash map, and then recurse. Next thing is last name, right? And then this is the remaining elements. Pull it out, right? Match on it. There's name is last name, type is string, okay? There's the key. Pull out the value from the actual element. summon the writer, write it in. Next up, age. Okay, pull it out. Right, name is going to be age, type is going to be int. Okay, get the key, pull out the value from the product element, summon the int writer. Sorry, this should be write int. Slide is wrong. And then finally, we recurse. Only the empty tuple is left. Voila, we're done. And guess what? We are back to the performance level of handwritten code because of this neat trick that we were able to do. So, okay, this is cool. This is cool. This is the code that ends up happening when we run it that way. By the way, if we look at this, if we squint hard enough, this is what it actually is, right? This is our key, this is our value, right? We got a key, we got the value, right? For each recursion, we got the key, the label value, wrote it to a string. Got the label key, label value, wrote it to a string. Label key, label value, wrote it to a string, right? Okay, that's what it works once everything's substituted. And by the way, that's just that, right? Those are our writers. And then, well, that's what it eventually becomes, right? So this is just a write to map. So it's basically the same code that gets swapped in, right? Doing the same thing typically yields the same performance results, right? So that's how we get the same performance that we got for the mutable data structure wrapped in the view. Okay. Now, before going further, how did I get this code? Right? Did I type this up myself? I did not type this up myself. How did I actually get this? There's a very cute method you can use to get the code that will actually get spliced by a macro, which is to write a printing macro. So here's a printing macro, super simple, that just takes an element inside, prints it, and just returns that thing. So whenever we want the recursive splicing of some kind of inline def, well, guess what? We just take this thing and we wrap whatever we're going to do inside of this thing, right? And then when the code is compiled, you have to make sure that the code is recompiled. Sometimes you might have to actually physically change the code to make sure that it's recompiled. But when you've got that, what will happen is that it will call this macro during the actual compile, right? You do svt compile, and it will call this macro. And during the compilation, it will print out your code that we've got over here. So very, very useful technique if you actually want to know exactly what's going on. Be warned, it is sometimes very gory. So sometimes you have to, manually mess around with what comes out of that thing until you can actually understand it yourself. Be warned. But this is still, I think this is a very effective technique for understanding how your code is getting spliced. Now, another unrelated note. So here's our derivation function, right? This is the fundamental thing that does our type class derivation. And we sort of assumed that there's this mirror attached. And then, right, we said person derives something, person derives write to map or whatever it is. But you don't actually have to do that. That's not strictly necessary. Here's why. You could actually, instead of requiring this thing to come in, you can use summon inline to summon the mirror directly inside the macro. And once you do that, you don't actually have to have a mirror in advance. Now, you need to rewrite this a little bit, right? We created this write to map on the outside, and then we defined this method on the inside. Well, if you want to summon a mirror, you kind of have to flip this around, and you have to summon it on the outside and create the object on the inside, which is actually why on the Dotty documentation, this is the approach that they use. because it's a little bit more flexible. So that's why normally you'd have to do person derives right to map for this entire generic derivation to get plugged in and for you to be able to write this person and its keys and values into a map. However, if you do it this way, you don't actually have to do derives right to map. What you could do is the second that this thing comes in, right? Remember that we put this thing in, we tacked it on using an extension method. That extension method had a using a right to map of T, which was a right to map of person. The second you do that, well, guess what? This entire machinery spins up into high gear and gives you your derivation. Okay, and by the way, 105 nanoseconds, same performance level. You don't have to do this if you do it this way, but you still can if you want, FYI. Oh, by the way, you can also use summon from instead of summon inline. Summon inline actually uses summon from, and the case in here is the actual thing that you're trying to summon, right? So we summon inline mirror of T. In this case, it's actually like a case. Summon from is quite powerful. You can actually summon from multiple kinds of things, or you can summon multiple kinds of implicits using it. Strictly more powerful than summon inline, I think, but you know, you can use either way of doing it. I prefer summon inline in most cases because it's simpler. The other thing to note is that, by the way, instead of doing an inline def on derived, you can do an inline given. That works as well. Oh, and FYI, this still works as well. It probably won't work for long because eventually these things are going to be deprecated, but you know, you can use implicit to actually do this also. My preference of all these is to use inline defs because givens and implicits can potentially, in some cases, create implicit resolution conflicts. So I don't use that route. I like implicit defs for this thing. So yeah, once you have that, essentially you define inline given right to map, and you get a derived right to map for every T. Very, very cool. Especially if you're writing a library and you don't want your user to be forced to actually put in, you know, derives your class. Super useful to use. Now let's look at some other examples of potentially slightly more complicated models. So, okay, here's, well, not really complicated, just slight extensions of what we're doing. Right? Let's say that we need to have a person who can be really old, like Star Trek's Q, who's 4 billion years old. His age doesn't encode into an int. So we want to have a new right to map of long, right? Pretty darn easy. User just defines this and it'll work. Same performance, right? The entire machinery of this just runs during compile time. Now, remember convertible age, right? Same kind of thing, right? We have a convertible age that we can define like this. Works just fine. Ooh, let's say we want to derive a right to map in order to reflect a list. Well, that gets a little bit more complicated. It certainly makes sense what the motivation is, right? You want to be able to have hierarchies with lists of things, potentially, right? So here's a guy that has a nickname or a list of nicknames, right? Everybody knows that Joe is Joseph and Joseph is Yosef, and they're all the same name. But anyway, so, okay, right? We want to be able to have a list of things represented in our domain model. Or we want to actually have a list of objects, which is going to translate it into a list of maps in the reflective case. Okay. Well, that gets a little tricky because we use this mutable method here. So what do, right? We need to actually define a kind of interface that will write it to a map, but if we don't write it to a map, what do? We don't want to write it into a map in this case, and we just want to pull it out in order to be able to put it into the list that we've defined, and we want to put that into a map. So here's a problem. We've conflated two use cases by defining this kind of API. We've conflated encoding with data structure, right? What we're trying to do is we're trying to write an encoder, but instead we're writing it into a map data structure. So, okay, fine, we can tease them apart by introducing various other switches and things like that that do various nasty things. But that's, again, if you're doing super performance-oriented code, you can go in this route because there isn't really much of a choice, right? If you really need to do this kind of thing, but and that'll work. 175 nanos, still pretty darn good. Basically the equivalent of having it done by hand. Okay, so here's the case where we have lists of other types, which need lists of maps and lists of things, of maps of things, right? We're starting to build a data structure that is essentially, it's a type hierarchy encoding of some kind. Okay, 347 versus 375, getting a little worse, but it's understandable, right? This is already recursive hierarchies of things. Okay, let's go immutable. Enough of this mutability garbage. Let's go immutable. What does this type derivation API look like for nice immutable things? Okay, well, the first thing is we want to actually be able to define what the thing looks like when it comes out of a write to map. A write to map has to be able to have a map come out of it, fine, right? That's where we store the reflective information coming out of our object. But we also have leaf nodes, right? Like strings and ints and potentially lists, right? Those things are not supposed to be maps. Those things are just leaf nodes that we write out of a recursive call. Okay, so simplest thing is to define some kind of ADT that defines this for us. Okay, so we called it a write output. Okay, what do we do with this thing? All right, well, here are the changes that we've made to what we've done before, where what we want to do is we want to say, okay, each recursive call is still going to produce a map. There are other ways to do it, but that's a simple way to do it. And we assign it to some kind of variable. And then what we do is we call the encoder, and then the recursion, instead of returning unit, will actually return pairs of keys and values, right? It'll return key value pairs. And the recursion will cons the key value pairs onto a map. Onto what map? Ah, this one. So at the very end, we cons the actual map, or because we splice this way first. So this is essentially the equivalent of a fold right. So this actually, as a result of all of this, this will happen first. And so we cons all the map keys onto the map. And so the recursion will cons key value pairs, right? First name and then Joe. Oh, by the way, it'll be leaf of Joe. Okay. And then the next one's going to be last name blogs, age 1, 2, 3. Fine. Okay. So once we've got this, and okay, here are type classes, right? All these different kinds of things. These are leaf type elements. Fine. And then, well, the only thing left is our convenience.write2map extension method that we want to be able to use to actually tack it on to any value t. In this case, we're assuming that it's a product, so we can assume it's a node type, right? So it'll contain a map, and then that's what we just return. Oh, FYI, Scala might complain about this because it doesn't necessarily know in here that this has to be a node type. So you still might want to handle the other case that you don't get a compile time warning. Anyway, so we put all this together and we get an immutable generic derivation API. That's neat. Wait a minute. Does it perform better than the mutable one? Let's take a look. Okay, here's the nicknames list thing. Performs better than, what was it, 175 nanos? Look at this one with a recursive hierarchy, right? 89 over 347, which is what we had with Immutable. So when I ran these benchmarks and when I looked at this, I was like, holy crap. Do I suddenly redo my entire talk, right? My assumption was that you needed mutability to be able to have the performance, but you actually don't, right? This thing actually does substantially better with immutable derivation than the mutable variation of it. So I don't understand how this is, right? Sort of, you know, we know that things like consing keys and values onto data structures generally more expensive than doing a mutable put, and we know that because we've seen metrics for it, and we know that in some cases in many cases, in fact, there are extra allocations that you need to do. However, that the performance numbers just don't line up with that theory or that thinking. So I don't know. It'd be interesting to talk to some of the people on the compiler contributors to actually figure out why this is, because I don't know, but it looks like that using immutable data structures in order to compose generic derivation, at least in some cases, performs substantially better than using mutable ones. And sort of the only explanation that I have why that is because the compiler is making certain kinds of optimizations. Again, because these inline defs are all happening in line during compile time. So it's possible that the compiler, that the Scala 3 compiler can make certain assumptions. That's my working theory, at least. Oh, by the way, right? Haven't we always been taught that doing a case match is expensive, right? This should be more expensive than that, right? I don't know, maybe this is a dynamic dispatch, potentially, but hold on a minute. Doesn't a case match require the allocation of an optional, right? And we need to do that. We need to allocate an extra optional and some other things that probably also involve dynamic dispatch. So I've always been taught that this is less efficient, but look at that. It goes down to 73 nanos if I do it like that. Same thing here. This is Wonderland. How can this be, right? How can this be more efficient than this? And again, my working theory is that the Scala compiler actually has certain optimizations that it can do for this thing. So anyway, this is really cool. So, this is a little bit like Alice in Wonderland. The rules work a little differently inside of here. So I don't know. I don't know how this can be more efficient than this. I have no idea, but it's cool. We're using more functional programming constructs and we're getting better performance out of them. And this always reminds me of a great quote by Flavio Persil, who is the author of Quill. He basically says, look, our intuitions about what performance should be are usually pretty darn bad, which is why the best approach is to measure things and then to go from there. And then, of course, the conclusion here is that using metaprogramming techniques with immutable things and functional things can have even better performance in some cases than mutable things. So, it's funny actually that I remember back in the day reading an XKCD on a functional programmer and a regular programmer talking to one another. And so, he's asking him, what's the big deal with functional programming? The functional programmer goes, recursion is its own reward, right? And so now suddenly those approaches have performance improvements, right? That's actually a way better answer. So now we're not just sitting here with our antics. We can actually do better than many of at least in certain cases than any of what the other approaches have to offer. So this is pretty cool. Not done yet. Sorry, there's a few other things I want to talk about. So first of all, let's extend this ADT a little bit. Let's say we want to introduce a notion of an array to an array element to the ADT itself. Okay, right? We want to introduce a notion at the top level. And let's say we want the ADT to be closed on itself, right? The only way to sort of represent data, the only way for data to come out is, through this leaf type. So the rest of it is closed on itself. And so, a map maps to the next kind of element of this ADT. Same thing with lists. Okay, fine. So then, right, we have to define our type class instances a little differently. Okay, fine. This is a leaf value, and because an array is a write output, so we have to map it into one. Okay, fine. Now let's define a funny little encoding function like that, and a little function like that, and voila, voila, voila. We have just built a JSON encoder. Surprise, surprise, right? It's got a little bit of work to do because typically we want JSON encoders to preserve the order of the fields, right? That's not what this thing does because it's a regular map. We want to do an ordered map, blah blah blah. But this is a JSON encoder that we just put together, right? With basically minimal changes to the data structures that we had from a generic derivation that I just whipped up together to write things into maps and lists, right? And now suddenly we have a JSON encoder. So this is pretty darn cool. It's ta-da! So the lesson to be learned here is that, once you understand generic derivation, immediately a new world of things that you can do basically opens up to you. Next up, coproducts, right? We needed to deal with coproducts. How do we deal with coproducts? Okay, right, we need to recurse over different kinds of coproducts. Okay, so we have a case for summoning a coproduct mirror or a sum mirror. Okay. Well, we need to recurse over it, right? We need to pull out the values of the type tuples in there. We don't care about the labels anymore because it's just the types. And once we recurse over the types, we want to pull out the fields in each respective one, right? If we have multiple kinds of things, right? It could be, a 3-part name or a 2-part name. What do we need to do? Well, what we need to do is we need to check during runtime, not during compile time, because during compile time, we don't know, right? During compile time, remember how, name was a 3-part name or a 2-part name. We don't know what that thing actually is during compile time. We only know what it is during runtime. So we have to do a check during a runtime. That check is something that we will splice in our macro. Our macro can't do it, but the code we splice in can do that. And that's what this is instance of thing does. So now, right here we go. We have a 2-part name and a 3-part name. This T here, name, is the only thing that this thing knows. Then once it recurses over this tuple, it then can splice in the actual code to match on the type during runtime. So, okay, here's our derive function, right? We start with the name type. There's that. Now, okay, so we splice in the different kinds of names that this could be, right? Name simple, name title, name dot title, there's a mistake there. Right, 2-part name or 3-part name, okay. So then, right, okay, fine. So there's what we splice into there. So we pull out the simple name and we say, okay, is it one of these? And again, this will run during runtime, not during compile time. Okay. So here's what we do. Here's the code that gets spliced. Okay. Next up, we recurse again. Okay, remaining elements of the tuple. Okay. Now, empty tuple is the only thing that'll be recursed next. Okay, voila. So this is the code that will actually get spliced in when your macro is done. Now, the case statements obviously won't exist. That's just for our being able to understand what's going on. So here's what the code becomes, right? This is the runtime code. Is the name this? Then summon writers for the 2 fields in name simple, first, last. Is it a title? Then summon the writers for title. Now, these things, this write to map actually will get spliced with the product derivations. And once all that's done, the full version of the code gets spliced in. I'm not showing that part because there would be too much to show for that. But anyway, here's what that looks like, right? When we actually say given write to map of name, this is what the product parts of the code will look like. And so there's the write to map. Okay, last part, and then I'll let you guys go. I want to talk about a Quill use case, or one of the many Quill use cases of generic derivation, which is actually a little different from most of the generic derivation cases you might see. Well, Quill generates queries coming out of databases and database tables during compile time. So let's say this is our data model, right? In the Hibernate lingo, we would call this a table per hierarchy data model, or table per coproduct data model, I think would be a better way to describe that, right? So this coproduct customer has a bunch of different fields and a bunch of different types, and we have a table that defines all the field values of those things. Okay, well, Quill, using Quill, we want to be able to actually generate a query, run it on a database, potentially while we're compiling, and then return the generated query that we've generated during compile time. Okay, right? Okay, fine. Imagine we have a simple database API that can run it, return a success or failure. Let's create the macro for that. By the way, one thing I like to do is use this .apply thing if it's a macro that does, or if it's an object that does a single kind of macro invocation. Anyway, so, okay, generate the query. Not sure how to do that, but once we've got that, we're golden, right? We're assuming that this thing is going to be a constant. And again, there are ways to not make that assumption, but for the sake of simplicity, I'm just assuming that this is going to be a constant that we know during compile time. Okay, we can create the database instance. We can execute the query. We can return the generated query. Okay, we just need to generate it. Now, this, by the way, this is a macro, right? This is a tasty reflect macro. So basically, the types that we're passing in are inside of this expr thing, right? This isn't an inline will call this, but this isn't composed with inline. So this is already one level down. Okay, so we need to generate the query. Let's generate the query. Okay, well, we need to get all the possible values of all the fields, or excuse me, we need to get all the names of the fields of all the possible values of customer. Right? So we need to get name and last name and CPU and name and fur color, right? Because we have different kinds of customers, right? You know, Yetis don't have last names, but they have fur, and robots don't have last names, they have CPUs, you know, whatever. So we need to pull out, we need to dive into customer, and we need to know all the variations of it and what fields they have to create our select statement. Okay, so let's do that. Okay, all the possible types of T, person, robot, Yeti, and all the possible values, once they're deduped, coming out of them. How do we do that? How do we do that? Okay, well, that's a sum mirror, and this comes out of a bunch of product mirrors. Can we summon mirrors inside of tasty reflect macros? As a matter of fact, we can. Slightly different syntax, but it'll still work. So here's what we do. Here's what we do. Let's define a function that will actually do that. FYI, here we're just getting customer, right? Or this is just the name of this T type, which is customer. That's our coproduct type. Anyway, okay, now, again, this is going to be our tasty reflect macros. All of them, by the way, require an implicit quote context, FYI. Now, let's grab that, and here is how we summon the mirrors. Instead of summon inline, it's expr.summon. Okay. Next up, well, what's the type of customer? Customer is a coproduct. Okay, let's pull out the different types of things that this coproduct thing can be. Person, Yeti, robot. Okay, fine. Then let's recurse over each one of those types and grab the fields, right? So here's, right, we grab these fields out of here, or excuse me, we grab fields out of person, and then out of robot, and then out of Yeti, right? And these are the recursions that this is going to be, right? So first it's going to be the tuple of all the elements, then the last two, then the last one, right? Similar to the kinds of recursions that we saw before, right? We start like this, gather the fields from, recursively call this base thing on person, and then pull out all the field types out of person. Okay, so now we've recursively called the base type again, and person is a product. So now pull all the fields out of person. Okay, right? Name, last name, those are the things that we will pull out, right? Recursively call this thing. Okay, and voila, name, last name, collect labels is the function that we call to pull them out. Recurse over the elements of this tuple. Again, this quotation syntax, by the way, that we're using, slightly different from the erased value syntax, but it does the same thing, right? We're still matching on the consing operator. Okay, pull out the const value of that, which is basically like doing the const value to string. It's a little different, this const value. Oh, here it is, by the way. It's a little different. We need to go a little bit lower level to actually understand it, but it works essentially the same way. So once we've got all this, okay, fine. We've got the last name. Okay, then empty tuple, and we're done. Go back to the base. So here's what we did in order to summon the labels from the products and coproducts of this customer object. Take that thing, generate the query. Here's the initial macro, right? That's how we define this query thing here. Okay, call this thing, right? An inline, every single tasty reflect macro starts with an inline. And an inline will actually go ahead and call that, right? And there's an apply, by the way. That's why I like doing this pattern. This is a macro call that does the dot apply. So this is going to call this. And then when you're doing a macro, right, it starts with an inline def, and then all the parameters, right, string, this becomes X per string, string is return. Basically everything is wrapped in an expression type. This is a more low-level way of programming macros, similar to Scala 2. But anyway, so here's what comes out. Hurrah, right? We have all the fields. Oh, we need to dedupe them. Robot has name and CPU, name and fur color, right? We just returned all the fields. We need to dedupe them too. Okay, needs a little bit of work, right? We need to pass these into an ordered set. Fine. Okay, done. Essentially, so here's a mechanism that you could use inside of a tasty reflect macro to traverse over mirrors and mirror types. And this is one of the ways that Quill uses it. And there we go, voila. You get this call, this query gets returned. And there's our original data model, right? Corresponding to the fields in our original data model. Here's the query. Okay, conclusion, if you're still here. So, in a world where the alternative to handwritten code or generated code is Java Reflection, Java Reflection will be a bestseller despite the high cost. Right? That's the reality. However, generic derivation is a game changer in terms of its ability to do things with a reflection-like API, which is similar enough. It doesn't require all sorts of low-level macro-esque shenanigans. You can mostly stay fairly high level, as I've shown you in some of the earlier examples. It's a reflection-like API that has the performance cost of essentially handwritten code because it runs during compile time and splices code. So this is really cool. I think that generic derivation indeed is the new reflection. Some links in case you're interested, and everybody, have a good evening.
Wow, thank you so much. That was an incredible presentation.
Thanks for having me.
Does anyone have folks that have questions that they want to answer? If you have time, Alexander.
Yeah,
or if
I've got time.
Get on, we can definitely close up. Anyone feel free to post in the chat if you've got questions or if you're just blown away, that works too.
Okay, I see some questions here. Yeah. Can we use macro stuff on Java classes as well? Unfortunately not. You cannot invoke Scala macros from Java classes because you're not really using the Scala compiler, you're using the Java compiler there, although sort of the Scala compiler delegates the Java compiler, but it doesn't really work. However, there is a however. Here's what it is. What you can do is that you can actually call the macros from Scala code, which is just a thin wrapper over whatever business logic you have. And you can then use that thin wrapper inside of Java code. Actually, this the Java user group, I'm talking to Martin Snyder of the Philly Java user group, and one of the things I'm thinking about is how to make a presentation on combining Spring and Quill, which is basically what you'd have to use. You'd have to use that strategy. And it's really not too bad. It's really not too bad. To use the Scala 3 Quill, you would need to find, I'd need to find a way to write mirrors for Java beans. I do not know how to do that yet. There are probably people who do. So it's certainly within the scope of possibility. Are summoned writers cached? So you actually can cache summoned things, because sometimes doing summoning like that does have some performance implications. Typically, you do that kind of thing when you're doing tasty reflect macros. I do have some situations in which I cache summon things. I do it. It works. There's a little bit of trickery in there, because when you're summoning things, and especially if you want to cache them in globals, well, you need quote contexts, and how do you reason about a global with that? So it can be a little tricky, but it's doable. Flavio. Have you had any compilation performance issues with Scala 3 macros? Does performance similar to Scala 2 macros? Scala 3 macros seem to perform better. They seem to perform better than Scala 2 macros. Certain kinds of things. So for example, in Scala 2 macros, actually summoning implicits inside of Scala 2 macros, pretty darn expensive. In Scala 3 macros, it is less. It is substantially less. Still, there's some reason potentially to cache those kinds of things, but it's not strictly necessary anymore. So that's nice. There are some other things that are also very, very nice. For example, doing things like writing out back values and writing out back expression values and pieces of AST. It seems to perform a little better in Scala 3, especially when you have many, many, many nesting layers. Scala 3 seems to be a little bit more robust than Scala 2 about doing that. So that's my experience there. It's a little bit more efficient. I don't know if it's not crazy more efficient, but it's definitely a little bit more efficient. Anyhow, Flavio, nice to have you, by the way. Any other questions? Can code generating macros be generated by a macro? There is a note about that in the Dotty documentation. There's a note about, I don't remember it off the top of my head, but there is a note about, what is it, multiply staged compilations or something like that. You can actually stage phases. I don't know how simple or difficult that is. I've just seen it. I'm not sure. I don't know. I have not played around with that functionality at all. I don't know what the implications of that, how much that can be done. I'm not sure. Any other questions?
All right. Well, thank you so much for your time, and thank you. Thank you. We have one more on the debugging experience, if you want
to. In the chat or?
Yeah.
Okay. Sorry. Have I not addressed
macros?
The debugging experience. The debugging experience leaves a little to be desired. The debugging experience, unfortunately for Scala 3 macros is not as good as Scala 2 macros. With Scala 2 macros, we can do very nice things with the breakpoints. They don't always work, but we can do it. In Scala 3, you can't do that. You can't do that. I'm using VS Code with metals, and I can't really debug Scala 3 macros. It's not there yet. That's basically the drawback of Scala 3 macros right now. The tooling experience, especially with debugging them, is not as good as it could be. So sad to say that. Anything else? Any other questions, comments, thoughts, anything? There's a lot of theory complex stuff in the presentation. How do you go about learning these? Dotty documentation and lots of trial and error. I have a talk on YouTube that I can repost where actually I go through a group of brave Drexel students that I introduced to many of the concepts in Scala 3 macros. I've got a video series on that that I can look up and repost on Twitter. Actually, come to think of it, if you just go to Dias Aquilius on Twitter, it's pinned right there. So if you just go there, you'll see the YouTube series. So I take a group of students through. It's both an introduction to Scala and an introduction to Scala macros. So it definitely, I try to cover a whole bunch of ground very, very quickly. But unfortunately, generic derivation is not on there. I haven't done a series on generic derivation, but a lot of the other concepts that I covered, so inline defs, how inline defs work, how splicing works, that a lot of that sort of stuff is on there. So if you want to know Scala 3 macros, it's a decent place to look. All right, actually I can, oh, okay. Any other questions?
All right, well then I think we are going to call it here. Thank you again so much, and thank you for everyone who attended.
All right, thank you everyone.